What LSST will do is go and see and measure galaxies that are as far away as 13 billion light years. And the data management system is trying to measure things at depths that have never been attempted before, to produce these extremely deep measurements of very faint objects within 1 billion years of the Big Bang, and at all intervals in between. So we're going to see not only these distant objects, but how objects have evolved over time. What has the structure of the universe been like at different epochs? How has it changed? How have individual objects changed? How have galaxies clustered themselves together? Essentially, we're going to see the whole evolution of the universe. And this depth and this time dimension are what I would refer to as the new sky. Through the process of repeated imaging of the sky over and over, LSST will achieve a data set where each part of the sky will have been imaged between 800 and 1,000 times. Through a digital process, we can add those images together. You get it without any vibration, noise, jitter, etc. A much more perfect image that goes much, much deeper.
First, you have to be able to build large optics, right? So very big telescopes require sophisticated techniques to manufacture the optics, to polish them and test them. Building optics the size and complexity of LSST, has only been possible in the last, say, 20 years or so.
One of the key technologies there is the construction of an 8-meter mirror, which is stiff enough to not require recalibration after every pointing, and are sitting on hundreds of fingers, and those fingers are adjusted to keep the shape in the ideal form to focus the light. And so you get the form, but you have this honeycomb that provides you with a very stiff glass structure. And then you put that on an even stiffer metal structure, and that allows you to shift, move, shift, move, shift, move.
The next thing would be building the silicon detectors, the CCDs, in a large enough quantity and with enough quality.
The instrument itself, the camera, is by far the largest and highest resolution camera that's ever been put on a ground-based optical telescope.
And then computers. The sheer amount of data that we take in is not something we could even have dreamed of processing 20 years ago.
Instead of just trying to look for an object, you'll get a scan of all the sky, where we are studying how to get scientific meaning out of this vast universe of data.
LSST is being designed to be a public survey. The data will be available so that any astronomer in the US or Chile will be able to go into the archive and pull out the data they want for their project. And so it's massively parallel astrophysics.
It's going to be a very large international collaborative project involving many different astronomy communities that are underpinned by a network layer that helps that data to be in multiple places very, very quickly. It really creates a multiplying effect of how quickly new discoveries are made.
Because we're hoping that hundreds, if not thousands of astronomers are accessing this data set at the same time, studying the asteroids of our own solar system to studying the most distant galaxies and the effects on the expansion of the universe.
The urgency is that we have determined pretty conclusively, of course, that there is dark energy and dark matter out there. The universe can't be expanding the way it is without something else being out there, and we know that. But we don't know exactly where it is, we don't know how much of it is, we don't know what it is. And with the LSST, we're going to be able to enable certain probes that will let us determine what its effect is with a great deal of precision, where its effect is most pronounced, and by doing that, we'll be able to learn a lot more about what it is.
And the idea was to go from this static sense of photography, moving in astronomy, into the motion picture era. But to do that with the same detail we're used to dealing with in the static image requires a huge jump in the ability to deal with the images and to analyze things automatically. There aren't enough grad students in the world to analyze all the data that LSST is going to take, right? It has to be done with much greater automation.
People, when they look up at the sky with their naked eyes, they see, even in the clearest nights, in the best places in the world, you see a lot of black and some areas of white. If you actually could look as deep as the LSST is going and see all of the objects that are out there, you would actually see more white than black. Right now there are fiber optic networks connecting the observatory in Cerro Pachon, Cerro Tololo, down in Chile, with Miami, and then up to the National Supercomputing Center in Illinois, NCSA. Those networks right now operate at about a gigabit per second capacity. The LSST needs to increase that capacity by 100-fold. And so we are working with AmLight and Reuna to increase the fiber optic capacity and the equipment necessary to move data at 10 gigabits per second or 100 gigabits per second by the time LSST is on board.
So it is a very high requirement, challenge that we have to fill, but it's not the only one, because also in terms of operation of the network, LSST will be a joint of effort of many institutions, and the idea is this work end-to-end from La Serena to a point in the United States. So we also have to do well in terms of collaboration, managing the network, so also it's a challenge.
These are very long distances that have to be traversed, and so the network has to be engineered in such a way so that then data can be moved on the network at a rate that guarantees that the data will reach its destination within a certain unit of time.
To detect transient events, as well as processing the quantity of that data over and over again.
And we send out alerts, millions of alerts a night to all over the world.
I don't think that they would be able to conduct these alert notifications in the same way if they don't have a network that they can depend on.
We do know there are things that explode quickly, like supernovae, novae, asteroids come whipping through the atmosphere. There's lots of things that happen rapidly.
Not just within one field of view, but we can track things from over here to way over there. We're taking one image, we're subtracting another 3.2 gigapixel image, and what's left are the things that changed. Things that moved, like asteroids, things that blew up, like exploding stars, supernovae. But the other thing is, we're observing the whole sky.
We have to do that within 60 seconds of the time this shutter closes. We need most of that 60 seconds for processing. So we've budgeted 4 seconds to get the data from Chile to the United States. There's actually 1 second to take the data down the mountain, and then 4 seconds to get it from La Serena, from South America, and our current path is through Sao Paulo, up to Miami, then to Champaign.
And then taking the results and then publishing those immediately in real time to the world. So astronomers anywhere in the world who have telescope time can actually go and point another telescope at those objects and determine not only are they in orbits that are near the Earth's orbit, but once you determine that orbit, you can determine, okay, 200 years from now, the Earth and that object will be in the same point. That's not a good day, right?
The interest in this project is just enormous. There are exciting education and public outreach applications. Google is one of our partners. It's just viewed as a tremendously valuable, both scientific and educational capability.
We're at the edge of what's capable today, and they're saying, well, we can use that. That'll push us.
So consequently, all the know-how that you will probably bring out of handling the massive data of LSST will have an enormous impact in society. That's why I think it's a unique project that will have very good consequences for mankind.
It's one of these instruments that is going to introduce a new paradigm as to how astronomy is done.
We're relying on the internet to get the data from Chile to the US, all around the US, then back out to partners all over the world. You know, this is an internet telescope of the internet age. When Bill Gates heard about LSST, he thought of LSST as the world's best peripheral. You know, this is computer vision taken to the nth power.
Imagine being able to see the entire universe on the computer waiting for you to explore. As images, as numbers, as movies, as any way you want to look at it. You can fly around the universe, you can look at the way that a particular supernova has exploded and see its light go to an intense flash and then decay over time. Anything you want to look at or evaluate in the known universe, you're going to be able to do that on the computer.